These are the answers to the Chapter 16 packet, Acid-Base Equilibria. Section 16.1, Acids and Bases, a brief review. The Arrhenius definition of an acid is that it's a substance that increases the concentration of H+ ions when dissolved in water, and that an Arrhenius base is a substance that increases the concentration of OH- or hydroxide ions when dissolved in water. So HCl, gas, dissolves in water to produce H+ and Cl- in aqueous solution, and solid sodium hydroxide dissolves in water to produce aqueous sodium and hydroxide ions. Section 16.2, Bronsted-Lowry acids and bases. The Arrhenius definition is limited to aqueous solutions. A more general definition of acids and bases is the Bronsted-Lowry definition, which involves the transfer of H+ ions from one substance to another. So water, whenever it accepts H+ ions, it forms the hydronium ion H3O+. Chemists use the symbol H+ and H3O+ interchangeably. You will also hear the H+ ion referred to as a proton. So when HCl reacts with water, we get hydronium and chloride. Here the HCl behaves as an acid because it donates a proton, and water behaves as a base because it accepts a proton. Does the Bronsted-Lowry definition of acids and bases require that the reaction take place in aqueous solution? No, it only involves the transfer of a proton, H+, from the acid to the base. So the smoke you see when solutions of HCl, hydrochloric acid, and ammonia, that smoke is solid ammonium chloride. The acid is HCl because it's a proton donor, and the base is NH3 because it is a proton acceptor. Here we have a reaction between ammonia, NH3, and water. Ammonia will accept the proton from water to produce ammonium, and the water loses a proton to form the hydroxide ion. So ammonia behaves as a base, it's a proton acceptor, and water behaves as an acid, it's a proton donor. A Bronsted-Lowry acid must have a hydrogen atom that it can lose as a H+ positive ion, and a Bronsted-Lowry base must have a non-bonding lone pair of electrons that it can use to form a bond with H+. So water is an example of an amphiprotic substance. What does that mean? On page 654 they define amphiprotic, a substance capable of acting as either an acid or a base. It will act as a base when combined with something more strongly acidic than itself, and it will act as an acid when combined with something more strongly basic than itself. So in this particular reaction we have HNO2, nitrous acid, behaving as an acid, water behaving as a base, and then the conjugate acid is going to be what happens when water accepts a proton. So the conjugate acid of water is the hydronium ion. The conjugate base is what happens when HNO2 loses a proton. So the conjugate base is the NO2-. Here we have water behaving as an acid, donating a proton, ammonia behaving as a base, accepting a proton. So when ammonia accepts a proton, the conjugate acid is ammonium, and when water loses a proton, the conjugate base is the hydroxide ion. So every acid has a conjugate base, which is formed by removing a proton from the acid. Every base has a conjugate acid formed by adding a proton to the base. So the conjugate base of hydrofluoric acid is the fluoride ion. The conjugate base of H2S is HS-. In all of these examples, we are removing H+ from the formula and producing either a neutral compound like pH3, or we're producing a negatively charged ion. But notice that the charge changes when you take off H+. So when you add H+, the charge changes as well. We go from methylamine to the methylammonium ion, CH3NH3+. Cn- becomes HCN. So we're adding H+, and we're changing the charge as we do it. Notice that the last three entries in these tables, HCO3-, HPO4-2-, and water, those are amphiprotic substances that are capable of either losing H+ to be an acid or accepting H+ as a base. The hydrogen carbonate ion, also known as bicarbonate, can give up a proton to produce carbonate and the hydronium ion, or it could accept a proton to produce H2CO3, carbonic acid, and hydroxide. So again, acting as both an acid and a base. So the words that go in this blank, the stronger an acid is, the weaker its conjugate base is. The stronger a base is, the weaker its conjugate acid is. You could have reversed those words and that would still be a true statement. On page 656, the stronger an acid is, the weaker its conjugate base, and vice versa. And you can see on page 667, here are examples of a strong acid on the left, in which the molecules are completely dissociated into ions, and a weak acid on the right, in which the molecules are only partially dissociated into ions. The difference between a strong acid and a weak acid in terms of how they behave: a strong acid completely transfers its protons to water, leaving no undissociated molecules in solution. A weak acid only partially dissociates in aqueous solution and therefore exists in the solution as a mixture of the acid and its conjugate base. Again, this information is on page 656. You should memorize the 7 strong acids that can be found on page 125, and they are hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, nitric, and sulfuric. So these are the 7 strong acids. On page 667, you can see examples of weak acids. So chlorous, HClO2, hydrofluoric, HF, nitrous, HNO2. So any acid that's not on your list of 7 strong acids, any other acid must be classified as weak. So chlorous acid, hydrofluoric, nitrous, hydrocyanic, hypochlorous, benzoic, acetic, carbonic, all of these are classified as weak acids. Why does the nitrate ion have negligible basicity? In other words, why is the nitrate ion not going to act like a base at all? And the answer is because the nitrate ion is the conjugate base of nitric acid, HNO3, which is a strong acid. Notice how the nitric acid completely dissociates into nitrate and hydronium. If you were to have nitrate acting like a base, it would have to react with water to produce HNO3 and hydroxide ions. That is not going to happen because the HNO3 is completely dissociated. So the reaction that occurs is going to be in one direction only, to produce nitrate ions. They're not going to go backwards. A strong acid completely transfers its protons to water, leaving no undissociated molecules in solution. Its conjugate base, in this case nitrate, has a negligible tendency to be protonated. So all of the 7 strong acids, their conjugate bases are not going to behave like bases in solution. Why is the fluoride ion, so F-, classified as a stronger base than the chloride ion, Cl-? Well, since chloride came from a strong acid, hydrochloric acid, and since fluoride came from a weak acid, the difference is that chloride has negligible basicity, just like nitrate we talked about, but fluoride is classified as a weak base. So fluoride could react with water to produce HF and the hydroxide ion because fluoride came from a weak acid. A weak acid only partially dissociates in aqueous solution and therefore exists in the solution as a mixture of the acid and its conjugate base. The conjugate base of a weak acid is a weak base. If you look on page 657, you'll see figure 16.3, and we can decide which of these substances is the stronger acid and the stronger base. So on the left we have an acid HSO4-. On the right we have an acid HCO3-. According to the figure, HSO4-, hydrogen sulfate, is a stronger acid. And then as far as bases are concerned, CO3,2-, carbonate, is a stronger base. So we put a capital A and a capital B under the stronger acid and base. We put a lowercase a and b under the weaker acid and base. The strong acid and strong base will react, and therefore this equilibrium lies to the right. So it's going to be the stronger acid and base reacting together, driving the equilibrium toward the right. In our next example, we're comparing the acidity of water and H2PO4-, dihydrogen phosphate. Dihydrogen phosphate is the stronger acid, hydroxide is the stronger base. So a capital A and a capital B, this reaction is driven to the left as far as the equilibrium is concerned. In our next example, we're comparing the acidity of ammonium versus water. Ammonium is a stronger acid than water, and hydroxide is the stronger base. So capital A and capital B, this reaction is driven to the right in terms of the equilibrium. Now we're comparing the acidity of H2S and the hydronium ion. The hydronium ion is a stronger acid. HS- is the stronger base. Once we identify with capital A and capital B, this equilibrium would lie to the left. And then finally, the stronger acid between acetic acid and HPO4-2- is that acetic acid is the stronger acid and phosphate is a stronger base. So capital A and capital B, this equilibrium would lie to the right. Section 16.3, the autoionization of water. We have already seen that water is amphiprotic, capable of acting as an acid or as a base. Write an equation to show how one water molecule can donate a proton to another water molecule. So the product of the reaction is hydroxide and hydronium. So in pure water, we have an equal concentration of hydroxide and hydronium ions. The equilibrium for the reaction we just wrote is strongly favored toward the left because the value of the equilibrium constant, Kw, is very small. At 25 degrees Celsius, Kw is 1 × 10⁻14. So we can write the autoionization of water as water splits into H+ and OH-, and this is a very important relationship that allows you to calculate the concentration of H+, OH-, pH, and pOH. In neutral solution at 25 degrees Celsius, H+ and OH- are equal, and their concentrations are 1 × 10⁻7 moles per liter. In an acidic solution, H+ is greater than OH- as far as the concentration. In a basic solution, the concentration of H+ is less than that of hydroxide. So now we're going to fill in the table with the missing information. 1 × 10⁻14 divided by 4 × 10⁻7 gives us 2.5 × 10⁻8. So because our concentration of H+ is greater than that of OH-, we have an acidic solution. 1 × 10⁻14 divided by 1.5 × 10⁻6 gives us 6.7 × 10⁻9. Since our concentration of hydroxide is greater than that of H+, we have a basic solution. And the numbers for the remaining values are 4.0 × 10⁻7 for the concentration of hydroxide. That solution is basic because hydroxide is greater than H+. And then finally 3.3 × 10⁻6, our concentration of H+ is greater than that of hydroxide, so that solution is acidic. Section 16.4, the pH scale. pH is defined as the negative logarithm in base 10 of the concentration of H plus or hydronium. So the pH is the negative log of the H plus or hydronium concentration. When the concentration of hydronium or H plus is 1 times 10 to the negative 7, the pH is 7. Only the numbers to the right of the decimal are the significant figures in a logarithm. So when the value of the concentration of H plus has 2 sig figs, the pH should have 2 decimal places. Now, as the concentration of H plus increases, the pH will decrease. Other things we have besides pH is we have what's called pOH, which is the negative log of the concentration of hydroxide. We also have what's called the pKw, which is the negative log of the Kw. That would be 14. So pH plus pOH equals 14 at 25 degrees Celsius. So in this table, all you have to know is one of the 4 quantities to be able to calculate the other 3. The pH would be the negative log of 2.5 times 10 to the negative 5, and that works out to be 4.60. To figure out the concentration of hydroxide, we could do 10 to the negative 14 divided by 2.5 times 10 to the negative 5, and that math would give us 4.0 times 10 to the negative 10. The pOH is 14 minus 4.60, so we get 9.40. Another way you could have gotten the concentration of hydroxide is you could have just figured out the pOH and then done 10 to the minus 9.40 on your calculator. This solution is less than 7 as far as the pH is concerned, so it is acidic. Now to get the concentration of H plus, in the first column you would do 10 to the minus 7.92, which gives you 1.2 times 10 to the negative 8. Then you could find the concentration of hydroxide, 10 to the negative 14 divided by H plus will give us 8.3 times 10 to the negative 7. And then 7.92 subtracted from 14 gives us a pOH of 6.08. This pH is higher than 7, so it's basic. Again, similar types of calculations for the third and fourth row as far as the table is concerned. I'm going to go ahead and fill in these numbers, and then you can check to make sure that you understand how to calculate these values. On page 664, there is a figure that gives you a variety of indicators and their colors. So we're going to take a look at solution number 1. It says methyl orange is orange and methyl red is red. So here in the diagram, if methyl orange is orange, then the pH is going to have to fall in the range where methyl orange transitions from red to yellow. And methyl red being red, it has to be less than around pH 5. So I'm going to estimate that the pH is approximately 4 for solution 1. Solution 2, I highlight that methyl red is orange and bromthiamyl blue is yellow. So therefore, if methyl red is orange, the pH is approximately 5, and you can see bromthiamyl blue would be yellow at that particular pH. So solution 2 has a pH of around 5. In solution 3, if bromthiamyl blue is blue and phenolphthalein is colorless, that would be approximately a pH of 8 according to the chart. So solution 3 has a pH of around 8. And then finally solution 4, if phenolphthalein is pink and alizarin yellow R is orange, I would estimate the pH to be approximately 11 for solution 4. Section 16.5, Strong Acids and Bases. Explain why double arrows in opposite directions are not used in the reaction shown above. This is one of your 7 strong acids. This is nitric acid. So double arrows are not used because nitric acid is 100% dissociated. There is no equilibrium situation with a strong acid. Chloric acid, which is HClO3, is also a strong acid. So the products are the hydronium ion and the chlorate ion, ClO3-. With strong acids, The concentration of H plus in solution is the same as the concentration of the acid itself. This is not the case with weak acids, and we'll talk about that in the next section. So the pH is simply the negative log of the concentration that you're given. The negative log of 0.50 is 0.30. The negative log of 0.0075 is 2.12. So we have a smaller concentration of hydronium, and therefore we have a higher pH. Our next two examples have even smaller concentrations of HCl, and we take the negative log, we get a pH of 5.47 and 7.82. Is there something wrong with having a pH of 7.82 for hydrochloric acid? That doesn't quite make sense. So is this value the correct pH of the solution? And the answer is no. So here's the deal. The value of 7.82 is not the correct pH. Since you have hydrochloric acid, which is a strong acid, you cannot dilute a strong acid with water and turn it into a base. So the pH of a very dilute acid solution will eventually be close to 7 because it'll be so dilute it has the same pH as pure water. So we've already gone from the concentration of the acid to the pH. Let's go in the opposite direction. If we're given the pH, then the concentration would simply be 10 to the minus whatever the pH value happens to be. So 10 to the minus 0.72 is 0.19. 10 to the minus 2.04 works out to be 9.1 times 10 to the negative 3, and the other two concentrations are even more dilute because we are raising 10 to the minus a larger number. Now this is still an acid. We're just simply showing you that you can go from pH to concentration. All right, so now let's talk about bases. The most common strong bases are the hydroxide compounds of the alkali metals, such as sodium hydroxide and potassium hydroxide. Other strong bases include soluble hydroxide compounds like calcium, strontium, and barium hydroxide. So the negative log of 0.25, that's our concentration of hydroxide. The negative log is 0.60. The pH is 14 minus 0.60, so we get a pH of 13.40. Now we have a potassium hydroxide solution. The concentration of hydroxide is 0.005. Take the negative log of that. The pOH is 2.30. 14 minus that value gives us a pH of 11.7. Now it says pay attention to the concentration of hydroxide in the last row. The concentration of hydroxide is not equal to 0.0050 because calcium hydroxide produces 2 moles of hydroxide for every 1 mole of solid. Our concentration of hydroxide is twice as much. It's actually 0.01. The negative log of 0.01 gives us a pOH of 2 and a pH of 12. A few more examples of hydroxide calculations in pOH. If the pH is 10.23, 14 minus that gives us a pOH of 3.77. 10 to the minus 3.77 tells us that the concentration of sodium hydroxide is 1.7 times 10 to the minus 4 moles per liter. 14 minus 12.34 gives us a pOH of 1.66. 10 to the minus 1.66, concentration is 0.022 moles per liter. Now since strontium hydroxide has 2 moles of hydroxide for every 1 mole of strontium hydroxide itself, even though our pOH values are the same as they were before, the concentration will be half as much as it was before. Again, half as much because we get twice as much hydroxide from 1 mole of solid. With sodium hydroxide, it's a 1-to-1 ratio. With strontium hydroxide, it's a 2-to-1 ratio. All right, section 16.6, weak acids. So which of these diagrams represents a weak acid? Well, the one on the right is completely dissociated That's a strong acid. The diagram on the left is only partially dissociated into ions, so that is a weak acid. If we represent a generic weak acid as HA, then the equation for the ionization of HA in water is HA dissociates into H plus and A minus. Now you also could have written HA plus water to produce hydronium and A minus. We're using double arrows because it is a weak acid, so therefore it's only partially dissociated into ions. Equilibrium constant that we're going to call Ka, the acid dissociation constant, concentration of H plus times concentration of A minus over the concentration of HA. The Ka is called the acid dissociation constant. You can see this on page 666 in your book. You can write either H plus or you can write hydronium in that expression. You also will see this formula, the Ka, on the equation sheet that they give you on the AP exam. Which of these two substances has a stronger acid? Justify your answer. Well, nitrous acid has a Ka value which is larger than the Ka value for hydrocyanic acid. So therefore nitrous acid is a stronger acid because it has a larger Ka value. Now many weak acids can contain what's called the carboxylic acid group, which has the formula CO2H. The acidic hydrogen atom is the one that's directly attached to the oxygen. So I'm going to circle the acidic hydrogen atom on all three of these structures. If you are given the concentration of a weak acid and you're also told the pH of the acid, it is possible to calculate the value of Ka. So that's what we're going to do in this problem. Nicotinic acid, also known as niacin or vitamin B3, has the structural formula shown at right. Its formula can be written as HC6H4NO2. So the equation for the dissociation of nicotinic acid in water would be to write the formula of the acid, double arrows, and then H plus and C6H4NO2 minus. So the Ka expression would be concentration of H plus times concentration of C6H4NO2 minus divided by the concentration of the nicotinic acid molecule. We are told that a 0.020 molar solution of nicotinic acid has a pH of 3.26. This is a weak acid. Calculate the concentration of H plus in this solution. So we are not going to take the negative log of 0.02. We have to figure out how to get the concentration of H plus from the pH. So 10 to the minus 3.26 is 5.5 times 10 to the negative 4 moles per liter. And now that we know the concentration of H plus, we can use an ice table similar to the one used on page 668 to determine the concentrations of all three species in solution. So the original nicotinic acid, what is its concentration? What are the concentrations of H plus and C6H4NO2 minus? Let's go ahead and make our ice table similar to the one you see here on page 668. So we know that the concentration of H plus is 5.5 times 10 to the minus 4. And because of the stoichiometry and the 1-to-1 mole ratio between the products, the concentration of the A minus ion, the C6H4NO2 minus, the conjugate base, is the same. Now the concentration of the nicotinic acid has decreased by that same value. And when you do 0.02 minus that rather small number, you get 0.019. So now that we know the concentrations of all three species in solution, we can calculate the value of Ka by plugging these three numbers into the acid dissociation constant expression. And when we do that math, we get Ka is equal to 1.6 times 10 to the minus 5. On page 669, we have a formula for the percent ionization. We're going to calculate percent ionization by taking the concentration of H plus at equilibrium divided by the initial concentration of the acid times 100. So in our case, the nicotinic acid has a molarity, a concentration of 0.02. The concentration of H plus we figured out was 5.5 times 10 to the negative 4 moles per liter. And so our percent ionization is 2.8%. This shows you that it's a weak acid. Only about 3% of these molecules are ionized in solution. Now, we've already calculated the Ka if we were given the concentration of the weak acid and the pH. What if instead we're given the concentration of a weak acid and its Ka value? Can we calculate the pH of the solution? Yes, let's go ahead and do that now. So the equation for the dissociation of hypochlorous acid, HOCl, in water is that it produces H plus and the hypochlorite ion OCl-. The acid dissociation constant, Ka, so H plus times OCl- over HOCl. So we're going to be given the Ka and we're going to have to solve for the pH. The Ka works out to be 3.0 times 10 to the minus 8. So we're going to have to, in our ice table, figure out what the concentration of H plus is. Once we know the concentration of H plus, then we can take the negative log and find the pH. So here is our ice table. This expression on page 670 for a similar problem leads to a quadratic equation. Are we going to have to use the quadratic? Thankfully, no. We can make the assumption that x, which is in the denominator, is very small, and so therefore we make the simplifying assumption that x is smaller, much smaller, than the initial concentration of the acid. So we make our simplifying assumption x squared over 0.02 is all we have to write. And we can set that equal to the Ka, which we were given, 3.0 times 10 to the minus 8. So now what's the next step? Solve for x, then take the negative log of that value, and that will be our pH. So x works out to be 2.4 times 10 to the negative 5 moles per liter, and the negative log of that gives us a pH of 4.62. So as you can see, 2.4 times 10 to the minus 5, which is our concentration of H plus, is much smaller than 0.02. So our assumption to ignore the x in the denominator was a valid assumption. As a general rule, if the percent ionization is less than 5% of the initial concentration of the acid, then we can make that simplifying assumption that allows us to avoid the quadratic formula. So let's go ahead and figure out the percent ionization in a 0.02 molar solution of hypochlorous acid. Remember, our concentration of H plus was 2.4 times 10 to the minus 5, so that gives us a percent ionization of less than 1%, 0.12. So yes, this assumption was valid. All right, let's move on to part K, in which we have to compare the pH of these two solutions, nicotinic acid and hypochlorous acid. Which one was stronger? And it says justify your answer not based on the Ka values, but based on the pH values. So the nicotinic acid had a pH of 3.26, the hypochlorous acid had a pH of 4.62, and they were both 0.02 moles per liter. So whichever acid has a lower pH is going to be the stronger acid. So the larger the Ka value is for an acid, the stronger the acid. But if two different acids have the same concentration, the stronger acid is the one that has a lower pH. The value of Ka for acetic acid is 1.8 times 10 to the negative 5. Let's calculate the concentration of H plus, the pH, and the percent ionization for each of the following solutions. So I'm trying to make a point here by showing you three different concentrations of acetic acid, 0.1 molar, 0.01 molar, and then finally 0.001. So as the concentration decreases, let's see what happens to the percent ionization. Something interesting happens. We'll take a look. Our first example is 0.1 moles per liter. So we have our simplifying assumption that we have x times x over 0.1, and that's equal to the Ka value. We go ahead and solve for x, and we get 0.0013 moles per liter. Take the negative log of that, and that will give us the pH, which works out to be 2.89. Now let's calculate the percent ionization. 0.0013 divided by 0.10 times 100. Our percent ionization is 1.3%. Let's do similar calculations for the other two solutions, and again, watch what happens to our percent ionization. So for the calculation for 0.01 moles per liter, we get a concentration of H plus of 4.2 times 10 to the minus 4. Now that's a lower concentration, which makes sense. We have a higher pH. That also makes sense. But look at what this percent ionization is doing. If we do the math of 4.2 times 10 to the negative 4 divided by the original concentration of the acid, that's interesting. Our percent ionization actually increases even though we have a more dilute acid. Well, if we continue the calculation, you'll notice that that trend continues. Here we have an even smaller concentration of H+. Here we have a slightly higher pH. And then we do the percent ionization calculation. It actually works out to be around 13%. So why is adding water to an acid actually increasing the percent ionization? Well, it is explained by using Le Chatelier's principle. When a solution is diluted, the concentration of the dissolved particles decreases, and the equilibrium will shift in the direction of the larger number of particles. So when you dilute a weak acid, you actually increase the percent ionization. You can see this trend on page 672, that as an inverse relation exists between the concentration of the acid and the percent ionization. So far we've looked at monoprotic acids with only one ionizable hydrogen atom, but there are polyprotic acids that can have 2 or 3 ionizable hydrogens. Now note that the second equilibrium constant, so Ka2, is much smaller than Ka1. And that's typical, that once you remove the first H plus ion, it becomes more difficult to remove the second H plus ion, because you're trying to remove a charged ion from a negatively charged anion, and so it's more difficult. There's a greater attraction. So if you have 2 or 3 ionizable steps for an acid, the first one is going to have the largest K value, and then they get smaller and smaller. As we've just seen, Ka1 is usually much larger than Ka2 or Ka3. So therefore, when we calculate the pH of a polyprotic acid, we can usually treat the acid as if it were monoprotic. This allows us to focus on the first ionization step as the only significant source of H plus ions in the solution. So in this question we have sulfurous acid, which has the formula H2SO3. The Ka values can be found on page 674. Notice that the Ka1 is rather large compared to the Ka2. So 1.7 times 10 to the negative 2 and 6.4 times 10 to the negative 8. Calculate the pH of a 0.10 molar solution of sulfurous acid. So for Ka1, that's the first ionization. That would be H plus, HSO3 minus. We'll go ahead and put in values of x and x. We have 0.1 minus x, and that's equal to 1.7 times 10 to the negative 2. Now I'm going to go ahead and solve for x. I had to use the quadratic equation, and I got that x, which is the concentration of H+, is 0.034 moles per liter. Since we're trying to figure out the pH of this solution, the negative log of 0.034 gives us a pH of 1.47. So I'm not worried about the second ionization step. I got all of my H plus from the first ionization step. Part 2, calculate the concentration of the sulfite ion, SO3 in this solution of 0.10 molar sulfurous acid. So remember, the first ionization involves taking off the first H. The second ionization takes off the second H. So where is the sulfite ion coming from? It's coming from this second ionization step. And what do we know so far? That after the first ionization, we have concentration of 0.034 moles per liter. Now some of that HSO3- is going to dissociate. So we have X coming from the second dissociation step, the second ionization step. X is a very small number because Ka2 is very small, and it's much smaller than 0.034, so we can make a simplifying assumption that our X is going to equal 6.4 times 10 to the negative 8. That's the concentration of the SO3 the sulfite ion. Now, as far as the calculation for H+, whatever additional H+ came from the second ionization step is not important. I can treat this diprotic acid as if it were monoprotic and focus primarily on the first ionization step. So look at that concentration of SO3 It's so small because the second ionization step has a very small value for Ka2. Okay, moving on to section 16.7, weak bases. If we represent a generic weak base as the letter B, the equation for the ionization of B in water would be that it has to be a proton acceptor. So when it steals the H+ from water, we get Hb+, and then we get hydroxide. So therefore, the equilibrium constant expression involves the concentration of Hb+ times the concentration of hydroxide divided by the concentration of the base. So B is the generic representation of a base. It could be ammonia or methylamine or anything. This Kb expression is also found on your equation sheet for the AP chemistry exam. Which of these substances is the stronger base? Well, earlier we said that if you had a higher Ka value, you were a stronger acid. The same rule can apply for bases. Whichever has a higher value of Kb is the stronger base. So in this case, methylamine is a stronger base than pyridine because it has a larger Kb value. There are two categories of weak bases. We have neutral molecules like ammonia with an atom that has a lone pair of electrons that can accept H+. And then we have anions like carbonate that can represent the conjugate base of a weak acid. As we learned back in chapter 4, amines are organic compounds that contain a nitrogen atom with a lone pair of electrons capable of accepting H+. Examples of amines include methylamine, trimethylamine, and aniline. Circle the compound that represents the strongest base. Looking for the highest value for Kb means that methylamine would be the strongest base among these three. Now, coming from hypochlorous acid, which is HOCl, the hypochlorite ion is one example of a basic anion. It came from a weak acid, and the formula is OCl-. Another example of a basic anion which came from HCN, hydrocyanic acid, is cyanide, or Cn-. So each of these has a Kb value associated with it, and that tells you the strength of the base. So it looks like cyanide is a stronger base than hypochlorite because it has a larger value for Kb. Now earlier we have already calculated the Ka when we were given the concentration of the acid and the pH. Here we're given the concentration of a weak base and the pH, and it's possible to calculate the value of Kb. So we're given that there is a 0.25 molar solution of ammonia. We're given that the pH is 11.33. The pOH is 14 minus 11.33, or 2.67. The concentration of hydroxide would be 10 to the minus 2.67. and that works out to be 2.1 times 10 to the negative 3 moles per liter. And based on the dissociation reaction involving the weak base, there should be a 1-to-1 molar relationship between the hydroxide and the ammonium. So in the balanced chemical equation, there's 1 mole of ammonium produced for every 1 mole of hydroxide. So that concentration of ammonium is the same as hydroxide. Now we have 0.25 moles per liter for the concentration of ammonia. We already know the concentration of ammonium and hydroxide. So 0.25 minus X, in this case, minus 2.1 times 10 to the negative 3, gives us a concentration of ammonia at equilibrium of just slightly under 0.25. So 0.2479. If you rounded that number off to 2 sig figs, it would still be 0.25. All right, let's calculate the Kb for ammonia by doing concentration of ammonium times concentration of hydroxide divided by concentration of ammonia. And so we get a Kb value of 1.8 times 10 to the negative 5. So earlier we just calculated the Kb. If we're given the concentration of a weak base and the Kb, it's possible to calculate the pH. So we know that a solution of ammonia has a concentration of 0.050 moles per liter. Let's calculate the concentration of hydroxide, the pH, and the percent ionization while we're at it. There's our Kb expression. It's ammonium times hydroxide divided by ammonia. We have X and X for the concentrations of ammonium and hydroxide, and we have 0.050 minus X for the concentration of ammonia at equilibrium. And we set that equal to the Kb, which is 1.8 times 10 to the negative 5. As you can see, I've made the simplifying assumption that X is smaller than the concentration of ammonia, and therefore X can be ignored to avoid the quadratic. So we solve for X, and that equals 9.5 times 10 to the negative 4 moles per liter. So there's our concentration of OH. To get the pH, we have to get POH by doing the negative log of the OH concentration. So the POH is 3.02, and then 14 minus that value, the pH is 10.98. For percent ionization, that would be concentration of the ionized species, in this case the hydroxide, divided by the original concentration of the base times 100. So our percent ionization works out to be around 1.9%. So those three values represent the answer to part H. Sodium hypochlorite is a weak base. We have a 1 liter solution of sodium hypochlorite. It has a pH of 9.50, and we're going to calculate each of the following quantities. We are also told the Kb value for the hypochlorite ion. So we'll start with POH. 14 minus 9.50 is 4.50. The concentration of hydroxide would be 10 to the minus 4.50. That gives us 3.2 times 10 to the negative 5 moles per liter. And since we have a reaction involving 1 mole of HOCl, hypochlorous acid, for every 1 mole of hydroxide, if we already know the concentration of hydroxide, that is the same as the concentration of HOCl because of the stoichiometry and the 1-to-1 mole ratio. So now our next calculation is the OCl minus. What's the concentration of OCl minus in this solution? Might be helpful to make an ice table to figure this out. So far we know the POH of the solution, we know the concentration of the hydroxide, and we know the concentration of HOCl. On to our ice table. That will help us calculate the concentration of the hypochlorite ion, OCl-. Let's fill in as much as we can in the ice table. Now once we fill in this information, we realize that the concentration of hydroxide represents the plus X portion of this ice table. So minus x on the left side of the equation, that tells us that at equilibrium, the concentration of the hypochlorite ion is x minus 3.2 times 10 to the negative 5. Now we can plug in these three values and solve for x. Remember that the Kb was given to us. So there's the Kb expression for the hypochlorite ion. We plug in our information from the ice table. We set that equal to 3.3 times 10 to the negative 7, and we solve for x. When we do solve for x, we get 3.1 times 10 to the negative 3 moles per liter. So that is our concentration of hypochlorite. We are in a 1 liter container, so we have 3.1 times 10 to the negative 3 moles of sodium hypochlorite that was used to make this solution. How do we convert from moles into grams? Well, the 74.44 just came from the molar mass of sodium hypochlorite. So our answer for mass of NaOCl in the solution is 0.23 grams. Section 16.8, relationship between Ka and Kb. The dissociation of a weak acid HA might look like this. HA as a reactant, H plus, and A minus as a product. We've already seen the Ka expression before. Now the reaction of A minus with water acting as a base, we would have a Kb for this particular base that involves HA and OH minus on top and A minus on the bottom. If we add the two reactions together and we cross off the HA and the A minus, we end up with the dissociation of water. That would be the Kw expression. So that means that when you add two reactions together, you multiply the equilibrium constants together. So Ka times Kb equals Kw. The pKa plus the pKb equals the pKw, which is 14 at 25 degrees Celsius. Let's figure out the pKa value for each of the following acids. The negative log of 1.8 times 10 to the negative 5 is equal to 4.74. And the negative log of the other Ka value, 3.0 times 10 to the negative 8, gives us a pKa of 7.52. Now, which of these two acids is the stronger acid? Well, you would say acetic acid is the stronger acid because it has a larger Ka. Now we've learned that there's another trend. Except for comparing Ka values, you could also say the lower the value of the pKa, the stronger the acid is. Okay, so we know that acetic acid is a stronger acid than hypochlorous acid because it has a larger Ka value, or you could say because it has a smaller pKa value. Now what about Kb for the following bases? So acetate came from acetic acid and hypochlorite came from hypochlorous acid. To calculate the Kb, you could do one of two things. You could take 10 to the negative 14 divided by the Ka, and if you do that, you get these values. Another way you could have gotten it is to take the pKb, so 14 minus 4.74, for example, and then do 10 to the minus the pKb. Either way, here are the two numbers for the Kb for acetate and hypochlorite. Describe the relationship between the Ka for an acid and the Kb for its conjugate base. Well, they're going to be inversely proportional, because if an acid has a rather large Ka value, it would have to have a rather small Kb for the conjugate base. So Ka and Kb are inversely proportional to each other. All right, on the equilibrium section of the equation sheet for the AP Chemistry exam, now you should have a better understanding what a lot of these equations mean. Kc and Kp, that was chapter 15. Ka we've talked about in this chapter. Kb, Kw, the definition of pH and POH, and then the last equation down there or near the end, pH equals pKa plus log of A minus over HA. That's called the Henderson-Hasselbalch equation. We won't talk about that equation until chapter 17, but still, a lot of these equations should make a lot more sense to you now. All right, section 16.9, acid-base properties of salt solution. A solution of a salt can be classified as acidic or basic when an anion reacts with water to generate H plus or OH minus. This reaction is often called hydrolysis. Now these anions, chloride, bromide, iodide, nitrate, chlorate, perchlorate, and hydrogen sulfate, all of them came from the 7 strong acids that we talked about earlier. Do these 7 anions act as strong bases? No, we said they have negligible basicity. So they're not an acid or base. How do they affect the pH of a solution? Well, the answer is they don't. So these 7 ions act as neutral or spectator ions in any sort of solution. Acetic acid is a weak acid. Acetate is a weak base. So the hydrolysis of the acetate ion is acetate reacting with water as a base, as a proton acceptor, to produce acetic acid and the hydroxide ion. So sodium acetate behaves as a base, and a solution of sodium acetate would have a pH that is more than 7. So sodium acetate is a basic salt. Here we have HPO42-, which is amphiprotic. It could either behave as a proton donor, so an acid in reaction 1, or it could behave as a proton acceptor, a base in reaction 2. Well, will a solution of this particular ion, hydrogen phosphate, be acidic or basic? Justify your prediction. Well, on page 682 it says the situation is more complicated when you have amphiprotic ions. How do we figure out what they do in water? It depends on the relative magnitudes of Ka and Kb. So if Ka happens to be larger than Kb, the ion will behave as an acid. If Kb happens to be larger than Ka, the ion will behave as a base. So in our situation, since 1.6 times 10 to the negative 7 is the larger of the two values, a solution of sodium hydrogen phosphate should be a basic solution because its Kb value is larger than its Ka value. All right, now we have to write an equation to show how the ammonium ion, NH4+, behaves in water. Since ammonia is a weak base, that must mean that ammonium is a weak acid. So therefore we could show it either just giving off H+, or you could show it reacting with water but still producing hydronium and ammonia. Now the Kb of ammonia is 1.8 times 10 to the negative 5. Therefore the Ka for ammonium would be 10 to the negative 14 divided by the Kb. And we get a Ka of 5.6 times 10 to the negative 10 for the Ka for ammonium. Ions like lithium, sodium, potassium, calcium, strontium, and barium are not going to affect the pH of a solution. So the ions of alkali and alkaline earth metals, being relatively large and not highly charged, do not react with water and therefore do not affect the pH. According to figure 16.16 on page 683, how could something like iron 3+, behave as an acid? Well, in solution, the iron is going to coordinate to all of these water molecules, and when you have a highly charged cation, it pulls those polar water molecules strongly toward that positive ion. One of those water molecules, as the strength of the attraction between the iron and the oxygen increases, it weakens the bond between OH. So one of those H pluses is going to produce the hydronium ion. So an iron 3+ is actually a weak acid in solution. This is a summary table to help you figure out if a salt is acidic, basic, or neutral. If the cation is a group 1 cation or a heavier metal member of group 2, and the anion is a conjugate base of a strong acid like chloride or bromide, etc., then that salt would be neutral. So calcium bromide, for example, is neutral, or sodium nitrate is neutral. If instead you have a basic anion, so like fluoride or hypochlorite, with a neutral cation, so sodium fluoride or calcium acetate, that would behave as a base. And finally, if you have an acidic cation like ammonium, and you have an anion that's neutral, so like ammonium chloride or something like that, it could be acidic. So this chart just summarizes what you could have in terms of neutral, basic, or acidic. All right, our next section is section 1610, acid-base behavior and chemical structure. All right, the strength of the HX bond tends to decrease as element X increases in size. So what do I mean by that? Well, if you have a small, short bond between H and F, and you compare that with a rather long bond between H and I, the HI bond should be easier to break, and the HF bond should be harder to break in that particular pattern. So it looks like the higher the bond energy, the more difficult it is for that bond to break. So why is this relevant in terms of acids? Well, if you have a strong bond and it's hard to break, it's the breaking of that HX bond that will determine if it's going to behave as an acid. Since the HX bond must break in this process, the weaker the HX bond is, the stronger the acid HX will be. Said another way, the stronger the HX bond is, the weaker the acid HX will be. So since HF has the highest bond energy and requires the most energy to break, that would be a weaker acid than HCl. And then you could look at that as a comparison. Moving left to right across a period, you already know that electronegativity tends to increase, and moving top to bottom down a group, electronegativity tends to decrease. So which bond is more polar, HO or HF? Looking at the horizontal trend between HO and HF, since fluorine is more electronegative than oxygen, the HF bond is more polar than the HO bond. So why does that matter? Well, a molecule of HF, since it's more polar, is more likely to give up the H plus ions than a molecule of water. So HF is more acidic than H2O. So we have a vertical trend and we have a horizontal trend. The vertical trend is that as you move down a group, the bond becomes easier to break and the acid strength increases. The horizontal trend is as you go across a period from left to right, the polarity of the bond increases and the acid strength increases. So we're looking at both bond polarity as well as bond strength. Which atom is more electronegative, chlorine or iodine? Well, it turns out that chlorine is more electronegative than iodine. But how does this difference explain the difference in acid strength between HOCl and HOI? On pages 686 and 687, they talk about the trend in terms of electronegativity of this atom Y, which is directly bonded to oxygen. It says, generally, as the electronegativity of Y increases, so does the acidity of the substance. And this happens for two reasons. First, as electron density is drawn toward Y, the OH bond becomes weaker and more polar, which favors the loss of H+. And second, because the conjugate base is usually an anion, so like YO-, that anion is generally going to become more stable as electrons are being pulled toward Y. So we see this on the figure. We have hypochlorous acid, which of the four is the strongest acid, and then hypobromous, hypoiodous, and then finally water. So when you compare the electronegativity of chlorine, bromine, iodine, and hydrogen, since chlorine has a higher electronegativity and can pull electron density toward itself, that makes it a stronger acid. Now HClO3 and HClO are different because one of them has extra oxygens. So on page 687, many oxyacids contain additional oxygen atoms bonded to the central atom Y. And because they pull electron density from the OH bond, they make it more polar and make that bond between the H and the O easier to break. What is a carboxyl group? Explain how resonance helps to explain the stability of the conjugate base in a carboxylic acid. This is on page 688. Two factors contribute to the acidic behavior of carboxylic acids. First, the additional oxygen atom will draw electron density from the OH bond, increasing its polarity. And then second, the conjugate base is stabilized by resonance, and that can make the anion more stable, which is going to favor the formation of the acid. So, these factors affect acid strength. In summary, we have to look at the polarity of the HX bond, we have to look at the strength of the HX bond, and we have to look at the stability of the conjugate base X-. So all three of these factors can contribute to the strength of an acid. All right, well, that represents the end of the Chapter 16 packet. Thanks for watching.